So, good morning, everybody. Today we are going to continue on probabilistic retrieval, and I'm going to start with a few reminders before we proceed with the computations. This is the Bayes formula. Who is totally fine with it, understands it? Okay, on Zoom as well, raise your hands on Zoom. Do we have raised hands in the chat? Okay. The Bayes formula is super magic because it allows you to turn a conditional probability, A conditioned on B, to the inverse when you swap B conditioned on A. It's actually extremely powerful because very often what happens is that in real life, you want to estimate something that you don't know and you have absolutely no idea how to calculate it. For example, the probability that it rains, how would you calculate that? But it turns out that if in the reasoning you swap things, and instead of wanting to know whether it rains or not, you can try to reverse the thing and say, okay, if I had information, then what would be, no, sorry, if I knew that it was raining, you assume it's raining, and then you try to deduct information, and then you swap it. And very often you're able to compute things in a more easy way. In that case, for example, it's very difficult to estimate the probability that it rains if I have my umbrella, but it's super easy to estimate the probability that I have my umbrella if it rains, right? So you turn something difficult into something easy. And of course, because that idea of saying, okay, what's the probability that it rains if I don't have my umbrella, there's all kinds of philosophical questions regarding that. What does that even mean, right? But it can be very useful in order to build systems like this, as we will see. So I'm not going to go to the philosophical considerations. This is another reminder about what a random variable is. And again, I repeat, because this is extremely important and I cannot emphasize this enough, a random variable is not random and it's not a variable. This is extremely important to understand. It's not random, it's not a variable. It's not random because it's a deterministic function, in fact, a random variable. It's a function that associates every elementary event in our omega space to some value in a target set. It is a function. And it's not a variable because what is a variable? A variable is something you can replace with something else. For example, you can have a mathematical variable small x, and you can replace it with 1 or with 2 and so on, right? Or in programming, you can replace variables. But you cannot do that with a random variable, right? When you have the random variable, typically in uppercase, big X, big D, big Q, and so on, you cannot replace them with anything. They are what they are, right? It's just because these are just functions like that. So it's very important to understand that it's not random and it's not a variable. And for this reason, I'm going to be very careful with the notation of uppercase for a random variable, lowercase for a mathematical variable. And once you have understood that, then whenever something is in lowercase, small x, small d, small q, it means you can replace it with whatever you want because it's a mathematical variable. So whenever you have small d, for example, you can replace it with whatever you want. You can replace it with a book, you can replace it with this flyer, and so on and so on. It's a mathematical variable. All right, so this is to show that here I'm just taking an example that my target set, so the values of the random variable can be one of 3 colored shapes, and I assign one of these colored shapes to every element in omega, and I can infer a probability distribution on my target set, in that case on the colored shape. I can just infer it from the actual function big X, right? And all I need to do is sum over the elementary events that are mapped to a specific shape. That's the probability of that shape. But it's not the same P. P normally is only for omega. Whenever you say the probability of something, it has to be an event in omega. The moment you talk about probability about the random variable values, you need this subscript x, px, because then you have it on S, on the set S. Okay, so in terms of notation, again, if you want to really consider S to be your new omega set, so to say, then the probability distribution would be px, and then you have just yet another probability distribution. But typically, it can be easier to understand by using this notation instead, and to understand that now you still use the letter P because you are in omega, and x equal blue square is an element, is an event, sorry, in omega, right? So these are the two probability notations, and I'm going to use this one. Okay. So I repeated that because it's really super important, and I know that some of you might, last week, might have been a bit lost, and I want to make sure that everybody is following. So this is why I'm repeating these things. Okay, so the Bayes formula, random variables, are neither random nor variables. Next, the thought experiment that I told you about. I talked about it in terms of this parallel world and parallel Earth. Let me take a different way of telling it without parallel worlds. That might be easier. It's equivalent. Imagine you're Satoshi Nakamoto, and you have this million Bitcoins that you have access to, and you have the private key. So what can you do with it? Well, let's be crazy and imagine that I'm going to use all of that money to do this thing. I'm going to basically iterate heptillions, quintillions, whatever number of times using all of that money. And what I'm going to iterate on is something extremely simple. Every time, I'm going to pick a document in the million or billion documents that there are in my collection, web page, book, and so on. I'm going to pick a query among a database of, I don't know, 10,000 queries or 1 million queries. And I'm going to pick a person, anybody on the earth, and I'm going to go to that person, say, this is a document, take it, this is a query, and I would like a yes/no answer from you. Do you think that the document I just gave you is relevant to the query I just gave you? Yes or no? And then you collect the yes or no that gives you one data point. If you repeat that millions, billions, trillions, quadrillions, quintillions of times, you're going to end up with a huge relational table. On every row of that relational table, you're going to have one document in the first column, one query in the second column, and a yes/no answer in the third column. And you have heptillions of rows. Okay? So now that I've thrown my million Bitcoins as that, and I end up with that relational table with a heptillion rows with these documents, queries, and yes/no answer, can I actually use that in order to build something valuable? And the answer is actually yes. I can actually turn it into something valuable, right? Because the idea is that now that I have this huge table, let me assume that I assign a uniform probability distribution to the rows in that table that gives me an omega set. Then I can start writing down things like, what is the probability that the query is information retrieval? What does it mean? It simply means I pick a row at random, uniformly at random in my huge table, and I look at the query, is it or is it not information retrieval, right? Of course, you can compute it actually easily. It's just a division. You divide the number of rows that have the query information retrieval by the total number of rows, right? It's a classical way of computing a probability, typically in introduction courses. You can do it the same with document. What is the probability that the document is this? Well, you just count the number of rows in your absolutely gigantic table where this is the document, you divide by the total number of rows, and you get the probability that this is the document, right? But of course, you can write these things, but you can also write conditional probabilities, right? You can basically write any probability formula in that way. So this is, again, a random variable. So this is for, is it the documents such and such? Is it the query such and such? You can do the same with the random variable R. For example, you can say, okay, what's the probability? The answer is yes. Well, it's easy. Count the number of yeses and divide by the total number of rows. You have the probability, the answer is yes, right? But of course, this is boring. If all you do is this, like what's the probability that this is the document, this is the query, this is the answer, things get interesting if you start writing conditional probabilities. So if you compute, for example, the probability conditioned on a certain document and query that R is 1, who could write the SQL query if you have this relational table to do that? what would my SQL query involve? Who knows SQL? You learned it in relational databases, right? In the database modeling. So how would you compute a conditional probability just by counting? Well, you need to do a selection on the rows that have document small d and query small q, right? So you select from where document is d and d is q. So big D and big Q would be the name of the column, and small d, small q would be the actual thing that you're computing, the actual document in query. And then you get them. And then you can also, once you have selected, you can do a group by. You can do a group by R, and then you get yes and no, and then you have the total number for yes, the total number for no. And if you want to compute that probability, it's just going to be the division of the total number of rows that have yes, D, and Q divided by the total number of rows that have D and Q. For whom is that clear? This is really basic probability things, assuming, of course, I have this gigantic table. So you see how this is even related to relational databases. Who would have believed that? But anyway, if I could do that, and I have the computing resources to do something like that, I can actually build a Google. I can build a Google because all I need to do is whenever somebody sends a query in the Google search box, all I need to do is execute my SQL queries and run my computation. Of course, I need to do it for every web page that there is on the internet, but let's assume I have a supercomputer that does that. Then I'm going to compute the probability that the answer is yes for F and Q, for D and Q, and so on. Q, of course, is fixed. That's the query the user entered. And F, D, G, E, and so on. These are all my documents. And then I'm going to sort by score. This is my score. So what am I actually trying to return in a search engine like that? I'm trying to return the documents for which, whenever I asked a random human on the planet, with the query that I just received for the user and the document I want to return to the user, what are the documents for which the most people said, yes, that's relevant? It makes sense that this is actually the way to go, right? Because now you're returning the documents, the web pages, the top 10 to the user that actual humans said the most, this is relevant to the query. For whom is that clear? Okay. Now, I have news for you. I'm not Satoshi Nakamoto. I don't have 1 million Bitcoins. I cannot build that relational table, and I'm totally unable to compute these numbers. How do we do it? We can just be clever and find another way to do it. And now you might remember that what do we do in the impossible situation that I want to compute a probability like this, and I don't know how to do it, right? Like probability trains. The magic thought is the Bayes formula. Maybe we can use the Bayes formula in order to turn this thing here, so this formula, into something we can actually calculate without needing that 1 million Bitcoins and this supercomputer and asking every human on the planet to be a relevance judge, right? So this is, in fact, exactly what we are doing with the probabilistic retrieval approach. And so the reminder of the lecture and what we started next week is to try to apply this Bayes formula to find the magic trick to compute these probabilities without the need to ask humans and have supercomputing power. Okay, so as a prerequisite, I told you we model the documents as vectors of Booleans. It's not new to you. This is what we've been doing for a couple of weeks at the beginning of the course, right? We've assumed that we abstract a book as just whether or not it contains the words. We forget about the order of the words. We forget about the number of occurrences of the word. We just care about the number of occurrences. And this is where I stopped, well, shortly before I stopped last time, and there was a bit of confusion on that formula. And I can understand why there is confusion. There's every reason to be confused. There's plenty of random variables in there. There's plenty of mathematical variables. There's this big D, this small d, the subscript with K, and so on, this big product. So there's many reasons to be confused. So I'm going to take some time to re-explain that and be very clear about that. First, it's always a good exercise to take a formula and try to understand it, to make sure you do understand it. Big D is a random variable. Small d is a mathematical variable. Big D subscript K is a yes-no random variable. Small d subscript k is a mathematical yes-no variable. That's the first thing. So the first thing that it means is small dk, I get to replace with whatever I want. These are mathematical variables. I can replace them with whatever I want. So I can replace d with this flyer right there, or I can replace it with Polyban is unexpectedly working today. That was Marco's idea of a document, right? So imagine that among the billions of documents that I have in my database, this is the one document that I'm taking. Why? Because I want to compute its score, right? And of course, I need to do it with every other one of the millions and billions of documents, but in particular, I need to do it for that very document right there. And you see that in front of it is a small d because that's a mathematical variable, small d, so I can replace it with what I want. If I wrote it with big D, that would not be the same, right? That would mean something completely different. Okay, so now look on the right, don't look on the left yet. So on the right, you see the list of word semantic of small d, the actual sentence, where you have the order of the words. And below it, you set the abstraction as a set of words. So what is this abstraction? Well, it's just this vector of Booleans, right? So here I didn't write it as a vector of Booleans. I wrote it rather using these Boolean variables, mathematical variables. So d Polyban is basically the coordinate in my vector of Boolean that corresponds to position Polyban. So wherever Polyban is, maybe position 1234, I don't know. And there is a 1 at this position. Why? Because Polyban is in the document D, right? The same for is, the same for unexpected D, the same for working, the same for today, right? So I have 5 places in my million row vector of Booleans, 5 places where there is a 1. These are the 5 words that they are in the document. Everything is a 0. ETH, Zurich, information retrieval, computer science, and the millions of other terms that you could possibly have in your dictionary are all set to zeros. For whom is that clear? Okay. Now here's the assumption we are making, called the binary independence model or the naive Bayes assumption. Imagine that I want to compute the probability that if I pick a document at random in my heptadian row table, the document is exactly Polyban is unexpectedly working today. So of course, there's the way of computing it with this SQL select query. So select everything in the table where the document is Polyban is unexpectedly working today. You return the counts, you divide, and so on. But as we said, we cannot do that because we don't have the table. We don't have the way to have this table. So we need to find another way. And another way to compute the probability is of saying, well, the probability that if I pick a document at random, this is the one, it's going to be a product of probabilities. It's going to be the probability that the document I picked contains Polyban, and that it contains is, and that it contains unexpectedly, and that it contains working, and that it contains today, and that it does not contain ETH, and that it does not contain information, and so on, and so on, and so on. So the probability of n, if I use the set of word model, that's an exact formula, right? I can actually write the probability that D is this under the set of word semantic is exactly the same as the probability that it contains these 5 words and it does not contain any of the others, right? So far it's exact. Now here's the approximation. Imagine that we assume that whether or not a term is in a document is independent. The term occurrence does not depend on each other across terms. So it means that I can write it. You know that when events are independent, the product of their conjunction, the probability of their conjunction is the product of their probabilities, right? Probability of A and B is probability of A times probability of B, right? It's not always true. It's only true if the events are independent. Yes? Yeah, so there's 2 things in there. There are 2 things in what you say about the order. So I'm repeating because I don't think you had the microphone so that people hear us. You're worrying about the order of the words. There are 2 things. The first thing is that we are working on under the set of word semantics. Under the set of word semantics, we clearly assume the order is irrelevant. We don't care, right? If the documents have different order of words or different number of times they occur, they are the same. That's my first assumption. Because of this assumption, when I say the probability that did contains polyban and contains is and so on, under the assumption of the set of word semantics, that's an exact equality, right? The second thing about the order is the order in which you write this multiplication. But here it's only because multiplication is commutative, right? So because multiplication is commutative, I get to write it in any order that I want, right? But again, why can I write it as a product of probabilities? Because I assume they are independent. This is the naive Bayes assumption or the binary independence assumption. If I did not assume independence, I would need to add these vertical bars in there. I would need to say the probability that D contains polyban times the probability that D contained is conditioned on the fact that D contains polyban times the probability that D contains unexpectedly conditioned on the fact that it contains is and polyban. This is the chain rule, right? But if I assume that they are independent, the occurrences of the terms, then I can get rid of the vertical bars and the conditions and then just write it as a flat product of probabilities, right? So again, two assumptions. First assumption, set of words. I don't care about the order, I don't care about the occurrences. Second assumption, I assume that the occurrences of the term are independent from each other. Right? I know it's a crazy assumption, but you know, that happens. We can make crazy assumptions. They allow us to simplify things. Okay? So this is now who agree with the formula that is on the left under the two assumptions. Set of words and independence of the events. Okay. Now, can I formalize that a little bit using this small d, polyban, and so on that I have on the right? And the answer is yes, because I can basically rewrite d contains polyban like this, right? Who agrees with this? This is a random variable d polyban that is a yes/no that tells me yes or no, the document I'm looking at contains polyban. Then I can do the same with is, unexpectedly, and so on. Notice that it's a big D, so these are random variables, but these are Boolean random variables. This is the same thing. This is just rewriting the same thing that D polyban means D contains polyban. So D polyban equals 1 means D contains polyban. For whom is that clear? That step as well? Okay. And then I'm going to do something absolutely trivial, is that I'm going to replace these ones and these zeros with the small d blah, blah, blah. Here it's a pure mathematical trick because it's an equality, so I can replace them. For whom is that clear also? Okay. And this is it. So now you understand what's going on. What's important is to understand that when I write this thing, this is for one specific document, small d. In that case, that sentence, but I could do the same with any one of the other billion documents. But I always pick one in order to write the formula. And now you realize this is exactly that formula right there. It's exactly the same thing. I just did it on a particular example of small d. I could do the same with any other document. Of course, if I take an entire book, that's going to be probably thousands of ones here and less zeros, but the formula is always applicable. You're just going to have different ones and zeros on the right. That's all. Okay. So who now, where am I? Here. Who now is fully comfortable with that we can go on, continue. Okay, on Zoom too? Raise your hands on Zoom. Yes, some raised hands. Awesome. So you're following. Very good. This is actually general advice. It's always useful when you learn something, take the time to take a formula and squeeze it and turn it in all directions until you fully understand it. That's always a very good exercise, right? And if you still don't understand it, then just go and squeeze the lecture and make sure that you get the explanations or that the formula is making sense. All right. And of course, part of the reason why this formula makes sense is because of what I told you to always use this notation. E, big D equals small d and so on, because this now you can understand. Now, if you take the book Information Retrieval where they do not write it that way, they actually write it P of small d equals the product of P of small dk, or the same with the big D, then it's much harder to understand. But now you can because you know the difference between a random variable and a mathematical variable. Okay. So Now that I have done that, and I have my new random variables with the terms, Booleans, then I can also write something like this. What does that mean? It's just the probability that the document I picked at random contains the term k, based on the fact that it's relevant and query is q. But this is only true if small dk is 1, right? If small dk is 1, meaning that the document small d that I take contains the word k, then I'm looking at the probability that the document contains k. If, however, the document I'm looking at, small d, in that case, it doesn't contain Zurich, for example, so now if k is Zurich, then dk, small dk Zurich is 0. So then I'm looking at the probability that the document does not contain term k, knowing that the query is in Q and that it's relevant. Okay. So now let's get back here. This is our goal. This is the formula, the base formula written with R&D. This is the same formula where I can add everything conditioned on Q. It's just, you can see it as a renormalization. It's always true. Any probabilistic formula, you can rewrite it replacing with the same condition everywhere. It's just like some renormalization factor, basically, in your omega sets. Okay, and now we start squeezing as much as possible out of this formula. All right, and last time I did a first step in there, meaning that I noticed that if I write the division of the probability that R equals 1 over the probability that it is 0, that's called an odd, right? This is what we saw. It's the odds that it's 1 versus the odds that it's 0, right? Why do I do that? Because I want to get rid of the denominator here. This probability that my document is small d, given that the query is small q, I can get rid of it if I divide, right? So I can divide in that way, get rid of it, and now I get this division right here, and I can rewrite it in this way. Who is with me on that? I just expressed the odds. Why did I do that? The reasoning is this. If I rank by probability, it's the same as ranking by odds, right? If I told you, let's assume you have a skewed die that has more probability of doing 6 than 3 and so on. If I tell you that I rank the numbers by highest probabilities first and descending probabilities, and now I do the same, but instead of ranking by probabilities, I rank by odds, that it's going to be 6 or 3 and so on. I'm going to get the same list, right? Who agrees? Right? It's just a monotonous thing, right? The odds depends monotonously on the probability. So if I want to compute a score, it doesn't matter that I score on the probability or on the odds. So I'm going to compute on the odds, and then I got rid of one of the 3 factors. Then this is also an odd, right? It's again the ratio of the probability it's relevant versus not relevant, just only conditioned on the query being small q. So I can rewrite it as an odd as well, right? Okay. Now, this is where I can use my independence assumption. How can we do this? Well, this is because of the Bayes magic. D used to be on the right on the condition, on what we want to evaluate, and that we can't do anything about it. But now it's on the left because by the magic of the Bayes formula that we invoked, we now have D on the left and R on the right. So this is where we get to use our independence assumption, which means that we can replace the probability that D is small d with the product, because we assume set of words, we assume that the terms independently appear in the document, so we can plug this in there. So you agree that if this is true, this is also true. Here I'm just adding the condition of relevance and query being small q. It's exactly the same thing, just with the condition. Who agrees? Okay. So if I plug it in there, I'm going to click and that should happen magically. There you go, see? Now we have replaced the probability that my document is small d with the products of the probability that the document is either 1 or 0, but 1 or 0 depends on the specific small d that I take, right? If the small d was Polyban is unexpectedly working today, then if k is one of these 5 words, then small dk is going to be 1. And if k is another word, then it's going to be 0. And again, I insist, for that formula, small d and small q are fixed. Small d is a particular document that I'm trying to score. Small q is whatever query the user entered, right? And the uppercase letters are random variables. Okay, now this is just about commutativity of multiplication and division, right? I just reorganize my multiplications and division in that way, right? Just mathematics. All right. Now, again, this is a Boolean, right? Depending on the document D that I take, it's going to be 1 for some case, and it's going to be 0 for some other case. But it is Boolean. So what if we just partitioned the terms, right? Right here, these are the terms that are in my document small d, the 5 words. Polyban is unexpectedly working today. I'm going to put them here. All the other terms, different packets over there. Of course, it depends on the document small d, right? But for a specific document small d, I can partition in that way. All the ones in there, all the zeros in there. So this means that I can now partition in that way, where on the left, these are all the cases that do not appear in my documents. It's basically the entire dictionary except these 5 words, if this is the Polyban sentence. And on the right, I have the case. So there's only 5 of them. It's a product of 5 factors. Polyban is unexpectedly working today. And now, of course, I replace dk with 1 because I know I conditioned it on being 1, right? So what I have is the product on the left that k is not in my documents for all the words except these 5, times the probabilities that k belongs to the document, but only for these 5 words that are in my document small d, right? So again, the multiplication on the left is absolutely gigantic. It's the entire dictionary, but the multiplication on the right is super small. It's just these 5 words that are in my document. Who is following? Okay. It helps to have a concrete example, right? Because if you don't have a concrete example, it might seem abstract, but imagine you have this Polyban small d, and that helps a lot. All right, so what's next? We're going to give them names. It's like pets, right? So we're going to name them. But in order to name things, we need to know what they depend on, because whatever it depends on, I need it in the subscript. So what does this thing depend on? Well, it depends on k and on q, right? Variable small k, variable small q. Why not on big D, big R, big Q? Again, these are not variables. Big D, big R, big Q, these are just my random variables. These are not variables. So this is why it only depends on the mathematical variables, small k, small q. What it means is if I give you a particular k, like Polyban, must be 1 for which dk is 1. So if I k is Polyban and the query is information retrieval, small q, given k and q, I can compute this thing, probability equals dk equals 1, conditional r equals 1, q equals q. I'm just going to call it pkq, right? Sounds like a Pokemon almost, but anyway. And I'm going to call this one ukq, okay? That gives me what is called actually a contingency table. Just checking that in the chat, that's from earlier. See, yes, that's what's from earlier. Okay. So now this pkq and ukq, these are what I call this and this. And of course, I don't know them, right? I would need to evaluate them. I don't know. But anyway, I just give them names. And that gives me this table. So let's look at this table. It has 2 by 2. It's a 2 by 2 matrix. So I have a specific query and a specific term k. So pkq is the probability that the specific term I'm looking at, Polyban, for example, is present on a document given that it's relevant to query q, small q. ukq is the probability that the case term is present, knowing that the document is not relevant to the query small q, right? And now what is the probability that the case term is absent? That's 1 minus, right? It's a complement, right? The term is either absent or not absent. It's present or absent. So if pkq is the probability that it is present, then the probability it is absent is 1 minus. Where is my 1 minus? Here it's right there. Because if I have a 0, then this is the absence. So this is basically 1 minus pkq, and this is 1 minus ukq, right? Who is following? Okay, so now we have this contingency table, and we have to evaluate if we had the values of pkq and ukq, then that would be wonderful because we could actually calculate this. Now, we are going to assume that if a term, there's going to be a lot of simplifying assumptions. I have to warn you. You can question them, you can criticize them, you can say, okay, this one makes sense, this one doesn't make sense. I'm just giving you the assumptions. And then, of course, there is this debate. People agree or disagree on whether this assumption makes sense. Here is an assumption that some people like to make and that might be useful. If the term that I'm looking at, polyban, is not in the query, in my example, that's the case. The query is information retrieval, and the term is polyban. So if the term polyban does not appear in the query, information retrieval, then I'm going to outrageously assume that PKQ is the same as UKQ. Looking at here. What does that mean? It means that the probability that polyban is in my document doesn't depend on whether the document is relevant or not. Why? Because it's not in my query. So the fact that it's not in the query, basically intuitively, if polyban is not in the query, it shouldn't influence the scoring of the documents, right? Only the terms in the query, information and retrieval, should influence it. So this is why we assume if K is not in Q, then we have the same numbers, PKQ and UKQ, for that case. But if the term is in the document, we are not assuming that, right? Only if the term is not in the documents, right? Again, the intuition is this. Imagine I'm querying for information retrieval. Then typically what I want is the information retrieval book, maybe some documentation on Google, Bing, and other search engines, and so on and so on. But the sentence polyban is unexpectedly working today, I couldn't care less about it, right? So the idea is that for all the terms that I didn't write in my query, the odds of being present or absent are always the same regardless of the document I'm looking at, relevant or not. But do you see where this is going? Because if we assume that PKQ is the same as UKQ, this goes away, right? The quotient, if you divide. If you divide something by the same thing, you get one. So of course, the people making this assumption, they have a Hintergedanken, right? They are making this assumption because they want to make a lot of the factors go away, right? It's not innocent here. But anyway, so what does it mean if I assume that when QK is 0, so when K is not in the query, they are the same, it means that my quotient is 1. So it means that in this product here, there's a lot of 1s. It's going to be a 1 whenever K is in query Q. So that means that I can restrict the product to the terms that are in the query, because all the others, the factor is 1. Who agrees? Right. This is just rewriting the same thing under this assumption, right? Okay. Who agrees that now this product is a very small product now? Because I'm only summing over query terms now. The terms not in the query, they are gone, they are no longer here. This is a super small product now. This is really nice. We like that. Okay. And now there is another absolutely outrageous assumption. No, actually what's outrageous is that the book authors did not even explicitly make that assumption. They just silently dropped the Q and just call them PK and UK and not PKQ and UKQ. All I did is make it explicit to you. I'm telling you, if you read the book, you will see they dropped Q. Normally, they should have explained why they dropped the Q. So in essence, this assumption here, which is yet another assumption, consists in saying that the evaluation that the terms are present or not present in documents do not depend on the query, right? It's a lot to ask, I know, but typically when you have a very difficult calculation, you can ask for a lot of things in order to simplify it and then have a discussion, right? So let's assume that these quantities do not depend on Q and we just have PK and UK, okay? So that means I can just simplify by calling it PK and UK, okay. Now, of course, this is only assumed under the condition that K is contained in Q, right? Okay. So now, so I just call it PKQ, then I can write it in this way. Who agrees? I just replaced this red zone and this blue zone with actually PK, UK, right? Who agrees? It's the same? Okay. Right, okay, it looks complex, but again, this product is super small because there are only terms that are in the query now, because we have this and QK equals 1 in the sum. Okay. So, what are the terms in here? These are the terms, of course, that are in my query, but these are the terms that are in the documents. So polyban is unexpectedly working and so on, right? So it's a product over the terms found in the document I want to score. And now I'm going to use a mathematical trick. I'm going to multiply and divide by the same thing. It's a gigantic thing, but if I multiply and divide with it, then that works, right? Because multiplying and dividing by the same thing at the same time is the identity, right? So I'm going to divide the left by this awful formula on the left, and I'm going to multiply on the other side with exactly the same thing. Who agrees it doesn't change the results, right? So I'm going to divide and multiply with this, right? So this is what I get. And we're going to just look at the details of that left and right. So if I take this thing and multiply in here, what do I notice? Here is the same thing, right? So what I'm multiplying on has exactly the same thing. So I'm essentially, for every value of k that meets this condition, I'm multiplying this, sorry, I'm dividing this by this. This is divide with. So this is going to be the product of this divided by this. Who agrees? Right. But if I divide by this, it's the same as multiplying with swapping up and down, right? So I just, instead of 1 minus p, 1 minus u, I have 1 minus u here and 1 minus p here, right? Who is still following? It's a step-by-step thing. There's a million steps in there, but you need to understand every step. Now, what happened here? I'm basically multiplying this with this. What is the same here and here? Now it's the same factor that depends on k. Here and here is the same factor, right? So I'm multiplying the same factor, but the values of k's are different, and they are complementary. Because here, I'm doing it for the values of k's that are in the query and not in the document. And here I'm multiplying with the values of k's that are in the query and in the document. So if I bring these two products together, that's basically the union of this and this, right? Who agrees? The union. So the union of D contains K and D does not contain K is just, it goes away, right? Because the union of true and false is everything, right? So if I'm taking the union of K is in the document, K is not, then I drop the DK part. Now it's just a product for every query that I have in every term in my query. If it was in the document, it came from here. If it was not in the document, it came from here. But now I just, like, it's a Wiedervereinigung, right? I have all of them in there. Who also agrees? Okay. So we are getting there slowly. What is the time? Oh, it's time for a break. We're going to take a break. I didn't see it's already 11. So it's 3 past 11. So we are going to meet again at 18 past 11. Making sure you get your full 15 minutes. And then we'll continue with these formulas. And I warn you, at the end, there is a Netflix-style Deus Ex Machina. It's called in theater. Some big surprise of what is going to actually happen with these formulas. But I'm not telling you more than that for now. See you at 18 past 11.